So now let's talk about the constructability of the project. We've really tried to break down this into several different areas, one of which is understanding the complexity of the program. And the project team, both DWR and the other state water contractors that have assisted DWR in this effort, have gone to great lengths to really understand the complexity of this project and how it relates to other complex infrastructure projects that have been implemented not only in the United States but throughout the world. We've also gone to great lengths to establish a management structure that we believe is appropriate for this large program, and recent developments at the formulation of the Design and Construction Authority I'll be talking about in a few minutes. We've also spent a great deal of time developing confidence in our cost estimates. I'm going to go through in detail the 3 different cost estimates that form the basis of our program to date. And then finally to talk about how we plan to manage program risks for the overall program. But first, before I get into that, let's talk about some of the program modifications and mitigations that have been made along the way. And I've mentioned a few of these, like minimizing the environmental footprint. The intermediate forebay is a good example of that. We've reduced impacts to the Delta communities. Examples of that is moving the 3 pumping plants that were immediately adjacent to the Sacramento River down to DWR property near Clifton Court. We've maximized the use of public lands by realigning the tunnel alignment, so now that it passes under publicly owned lands or foundation-owned lands. We've reduced the size of the overall program from 15,000 CFS to 9,000 CFS, and we have been able to provide for gravity flow under certain conditions for the North Delta diversions. This gives you an idea of the footprint for the original canal that Roger was discussing with you. It's going to be approximately 1,400 foot wide footprint, spanning about 35 to 40 miles through the eastern side of the Delta. This would have cut a large swath, eliminating animal migration paths and also just connectivity for transportation and farming through the Delta. This footprint would have taken up about 19,000 acres if fully implemented. Now with the tunnels, we've been able to reduce the surface impacts by about 90%, with much of the facilities being below ground. We still do have the above ground intakes and also the pumping facilities. With the tunnels being approximately 2/3 of the constructed cost of this facility, we've spent a great deal of time looking at other tunnel projects throughout the world. I presented many of these examples to this committee back in January, just reviewing quickly for you. The last 2 projects listed here are the 2 largest tunnel projects in the world. We've met with all of these folks on here with the exception of the Eurasia Tunnel in Turkey. Quick refresher on tunnel boring technologies. At the far left, you have the cutter head that will be moving through the soil. The soil, through our preliminary investigation at tunnel depth, will be dense silt, sands, and clays, ideal for tunneling conditions, with the only potentially problematic issue is the water pressure that will be in front of the tunnel boring machine. So we're proposing to use what we call an earth pressure balanced tunneling technology to overcome that pressure and allow us to tunnel safely. Next along the line there, you can see the jacks that press against the segments as they're constructed, and then the segmental liner. That's a cutaway there. Normally you wouldn't be able to see that operation because there would be a shield protecting the workers inside the tunnel boring machine until the segments are fully erected. And then behind that you have the screw conveyor that brings out the reusable tunnel material, as we call it, places it on a conveyor, which transports it to a shaft to be brought up to the surface, land surface. So these are large tunnels that are proposed for this program. Even at 28 foot in diameter, these are larger than your normal metro tunnels. So we did spend quite a bit of time researching the capabilities of the tunneling industry and the contracting industry to design tunnel boring machines to meet our needs and also to construct these tunnels safely and efficiently. And so what we found here, this is a representation of where our tunnels will sit as far as the state of the practice for worldwide tunneling technology. So we feel that we're in the sweet spot of the large tunnel boring machines. There's a lot of experience with designing, building, and operating these size machines, a lot of successes. And then as you move out to the right side, you can see those 2 large tunnel projects that I mentioned, both the Seattle project and the Hong Kong project. Many of you are aware of the difficulties that the folks up in Seattle ran into with the Bertha tunneling machine. Those were eventually resolved, but it was approximately a 2-year delay in their overall project, but they did hole through and complete tunneling in April. We also, during the conceptual engineering effort, did look at the opportunities to go with a single bore tunnel. Right now we have 2 40-foot inside diameter tunnels. We did look at a single bore tunnel. We were estimating that in order to convey the full 9,000 CFS, that we'd need an inside tunnel diameter of approximately 56 feet, which would translate to a tunnel boring machine requirement of about 60 feet. So you can see that would be well beyond what the current tunneling industry has offered so far and successfully applied. And so that was one of our reasons for mitigating risk, at least on the tunneling side, was to recommend going with twin tunnels of a smaller diameter. Tunnel shafts will be utilized throughout the project, and this is because the delta is relatively flat. We'll be at depths of about 150 feet to the bottom of the tunnel. So we'll be using these shafts to allow us to launch the machines, which is to get it working, also to retrieve the machines at the end of their tunnel drives, and then to put all of the material and staffing and everything into the tunnels, ventilation, things like that. In long term, in the short term, the shafts will provide construction access. So in addition to these large shafts required for operating and maintaining the machines, we'll have shafts at midway locations and sometimes at specialized maintenance locations. These will be temporary shafts and will be buried, closed up and buried after construction is completed. The few remaining shafts, I believe there's about 3 of these different locations on Staten Island, Bolden, and Bacon Island that will allow DWR to get long-term access to the tunnels for maintenance, which is expected about every 5 to 10 years. So as we were developing our program plans for the overall management of the project, we also looked at other mega programs in addition to just tunnels, and this is a listing of the few that we did look at. Some of these you'll recognize pretty quickly. Some have very good reputations, like the Water Supply Improvement Program San Francisco is recently completing, and others have maybe checkered reputations, such as the Boston Big Dig. But we looked at all of these, we gathered best practices from all of these programs, and we've worked these into our overall program plans for implementing the project. So what are the lessons that we've learned from all of these experiences that we've been gaining from talking with others on their projects? First and foremost, proactive risk management, and first on that list is controlling the project scope. This will be first and foremost on our list of requirements. Often we see projects run into problems when they're shortly after they are authorized. A lot of additional scope is added to the project. Makes it very difficult to control your overall schedule and budget for the program at that point in time. Another item that we really put a lot of significance on is running an active and continuous risk management program and assigning risk to the appropriate party along the way. I'll talk a little bit more about that. But in difference to some of the other programs that we've studied, where risk management is kind of done as a one-off process, we plan on doing this as a living effort or process throughout the entire life of the program. Since 2/3 of the cost of the program, capital costs, are in the tunnels, we really need to know what the geological setting is. As I presented before, we have about 200 borings through the delta right now. That's not just for the tunnels, that's for all of the other facilities too. This is not enough to complete final design of the tunnels. We need to do a much more robust program, and a more robust program is planned and was covered in the environmental planning process. We have a 2-step program that will be implemented. We plan on collecting, depending on the ground conditions, upwards of 2,000 different samples of the ground, so we really understand what that is and able to document that in our contract documents. Finally, addressing long lead time items. This is really critical for these linear projects like high-speed rail, long pipeline projects, making sure that you have all of the rights of way acquired early on and that you have those in your control before you start issuing construction contracts. Utilities and coordination with outside agencies is going to be especially important in the Delta. We're going through a number of different communities, and we have to work with those counties, cities, and other localities as we move through their areas. And then finally, logistical issues. The Delta is relatively close to Sacramento and Stockton, but it is a very rural area, and we need to develop the sites before we begin to come in and work. So we'll be working on those early on. Program schedule. We currently have a program that will take approximately 16 years from initial startup through completion of construction, with an additional year or so of commissioning at the end of that. You can see staffing. We do not have a program office at this point. We'll be building one from scratch. We have sort of the nucleus of that with some staff and personnel, but it's going to take literally hundreds of people to successfully design and to construct and manage this program. So it'll take us a little while to staff up, but we think we can start design relatively quickly, about a 4-year design period. with the first construction starting about year 3 after we're given the approval to move ahead with the program.